Somebody clicks Buy on your online store. The page takes 3.1 seconds to come back. That is slow enough that people leave. So you go looking for the reason, and you find something awkward. That one click did not touch one program, it touched 5 separate services, each on its own machine. One of them is slow, the other 4 are fine, and nothing on your screen tells you which. This video is the mechanism that answers that in 4 small pieces of code. Start with what you already have, logs. A log line is a very small thing. It is one service writing one sentence into its own file on its own machine using its own clock. Now multiply that by 5. 5 services means 5 files and 5 clocks, and those clocks are never perfectly in step. They drift by milliseconds. Worse, nothing in any of those lines says which click it belongs to. Your one checkout is scattered across 5 files with nothing tying it together. Here's what that looks like. Every service logs the same way. Checkout writes Start Checkout. Auth writes Verify Token. Each line gets a timestamp, and each lands in a different file. Now try to answer the question. You search for the order ID, but auth never received an order ID. It only saw a token. So you line the files up by time instead, and look, the auth line has an earlier timestamp than the checkout line that caused it. The clocks disagree. So that is the trap, and it is worth saying out loud. A log line knows exactly one thing, what happened inside one service. It has no idea a bigger request exists because nobody ever told it. Which means writing more log lines does not fix this. What is missing is not detail. What is missing is identity. So we give the request an identity. This is the first piece of code, and it lives at the edge, the very first service the click arrives at. It is a piece of middleware, which just means a function that runs before every request is handled. It does 2 things. First, it looks for a trace ID in the incoming headers. Headers are the little labeled fields that ride along with every web request. If one is there, we keep it. If not, and for a brand new click there will not be, we mint one, a random string unique to this request. That one ID is the whole idea. It is born once at the front door, and from then on it never changes. Checkout hands the same ID to auth. Auth hands the same ID to inventory. Every hop passes it forward untouched to whatever it calls next. That is called propagation. And now every line in every file in all 5 services carries the same ID. Propagation is code you actually have to write, and here it is. This is the outgoing side. Every time this service calls another service, we take the trace ID we are holding and copy it into the outgoing headers. That is it. One header forwarded. The receiving service runs the middleware from before, finds the header, and keeps that ID instead of making a new one. Notice how fragile this is. One call that goes around this wrapper breaks the chain. An ID tells you which lines belong together. It does not tell you how long anything took. So each hop records one more thing, a span. A span is a tiny record about one piece of work. It has 4 fields, its own ID, the ID of the span that called it, which we call the parent, the time it started, and how long it lasted. That parent field is doing all the heavy lifting. Here is a span being created. We open a block, we note the clock on the way in, and when the block exits, however it exits, we note the clock again and subtract. We attach the trace ID, our own new span ID, and the ID of whatever span we were inside when we started. That last one is the parent. Then we hand the record to a collector, a separate service whose only job is to receive spans. And this is the other end.
The collector gets a pile of loose span records arriving out of order from 5 different machines. First, it groups them by trace ID, so it is looking at one request at a time. Then it builds a lookup from span ID to span. Then, for every span, it finds its parent in that lookup and attaches itself as a child. A span with no parent is the root. What falls out is a tree.
And when you draw that tree against a time axis, you get this: one nested bar per hop. How wide a bar is tells you how long that work took. Where it starts tells you when. The whole request is 3.1 seconds. Checkout's own work is 40 milliseconds, a sliver. Auth is 30. Payment is 70. And then inventory, and inside inventory, a single database query running for 2.9 seconds. Put numbers on it, because the numbers are the point. 2.9 seconds out of a 3.1 second request came from one call. 94% of the wait in one place. All 4 other services together are about 140 milliseconds. Before tracing, you would say the system is slow and start guessing. After tracing, you say this query is slow and go fix a query. Now, the honest part, because tracing still has 2 ways of lying to you. The first is a dropped header. If one service forgets to forward the ID, an old library, a call that goes around your wrapper, then everything downstream starts a brand new trace. Your waterfall simply stops there. The second is sampling. At real volume, you cannot keep every trace, so you keep a fraction, maybe 1 in 100, which means the request somebody complained about might be one you threw away. So the whole mechanism in 4 steps. 1. The edge mints a single ID for the request. 2. Every service forwards it, unchanged, to whatever it calls next. 3. Every hop records its own span, start, duration, and the parent it came from. 4. A collector hangs the spans on their parents and draws the waterfall. Jaeger, Zipkin, and opentelemetry all do exactly those 4 things.
If that made tracing click, hit like and subscribe. One concept all the way down to the code every time. There is a short version of this in the description if you want the quick cut, and no more sitting there at 2 in the morning guessing which service is guilty.